SwayamPrabha. Digital India. Educated India.
Hello everybody, welcome back to the series of lecture on elements of solar energy conversion. So far we have looked at the background that we require for this solar energy conversion techniques. Then we started looking at the flat plate collectors, which are the basic of the all kinds of collectors, and then we have looked at few variations of that. We did detailed thermal analysis, and in the last class what we started is the concentrating collector, and the first topic we took was the theoretical limit of concentration ratio, how much maximum concentration we can think of. Okay. Then any practical device can be weighed according to that theoretical limit. So, we are here at lecture number 24. So, in the last class what we have seen, the three dimensional concentrator can have C max, which is 1 over sin square theta s. Okay. That means that is the theta s is the half angle that the solar disk makes on the surface of the earth. Okay. So, this theta s, let me just repeat it, that it is the half angle the solar disk makes on the surface of the earth. And for 3D concentrator we have C max equal to 1 over sin square theta s. This we derived, right, and we have used the thermodynamical limit, and that is why it is called thermodynamic limit or theoretical limit for concentration ratio. Similarly, for two dimensional concentrator, okay, two dimensional concentrator means what? Suppose you have a, this is the sun and it is radiating all around. Okay. So, you can think of a two dimensional plane which is a circle and earth is somewhere on that circle. So, instead of sphere, this is a circle for 2D concentrator geometry. Okay. So, for 3D this is a sphere. We considered a sphere around the sun. Okay. So, this time we are considering a two dimensional circle. So, again similar way we can think of, we can write the total amount of radiation going out of the sun along the 2D plane. Okay. So, that would be your 2 pi r into sigma T s to the power 4. 2 pi r is what? The circumference of the circle. Earlier we have used 4 pi r square, which is the total area of the sphere. In this case, what we need to do, we have to take the circumference of the circle, and that is 2 pi r. R is the radius of sun. Okay. And the rest part, the sigma Ts to the power 4 remains the same. Okay. So, similarly, what we can find, the radiation intercepted by the aperture area A subscripted with A is 2 pi r sigma Ts to the power 4. This is the total amount across the circumference, and you have a fraction of that in the absorber, which is A divided by 2 pi r. This r is radius or the mean distance between sun and earth, right. So, exactly same way we are handling the fraction of radiation that are getting intercepted by the aperture area. So, following the same path, which of course I am not going to repeat, the C max, now let me subscript with 2d, will be 1 over sin theta s. Instead of sin square theta s, we have 1 over sin theta s. Okay. So, that is the theoretical limit for a 2-dimensional concentrator. Okay. So, here we must remember that C max 3d equal to 1 over sin square theta s and C max 2d, which is 1 over sin theta s. Both of these gives the upper limit or thermodynamic limit of concentrator optics. Okay. So, this is kind of a limit that can never be reached, because it requires that the receiver reaches the same temperature as the sun, which is impossible to achieve. Okay. So, a never achievable limit which can be used to compare the different concentrator optics. Okay. So, that means it is like a Carnot efficiency kind of limit which is never obtainable, but provides the theoretical upper limit. So, just to say that okay, if somebody says that some very large number, okay, let us say that 1 lakh times concentration ratio is achievable, whether you can believe him or not. So, that kind of limit this particular value puts. Okay. So, now for earth, this theta s, which is the half angle that the solar disk makes, that is 0.267 degree. Okay. So, on Mars it will be different because it depends on the mean distance between the sun and that particular planet. Okay. So, for earth it is 0.267 degrees. There is a slight variation as the distance between the sun and earth changes, but it is negligibly small. So, we can take the mean value which is 0.267 degrees. So, what we can see, the C max 2d which is 1 over sin theta s, you can substitute this value and you can see the approximate value will be 212. Okay. And similarly, C max 3d is 1 over sin square theta s, and that is approximately 45,000. Okay. So, two very important points here we need to make, that the 3-dimensional concentrator can have very high concentration ratio or CR, okay, and 2D concentrator has limited capacity of concentration. Okay. 212 is the theoretical maximum. So, in reality you cannot get beyond 50. Okay. And for 3-dimensional concentrator, the theoretical limit is 45,000. So, you can go well above 2000, 3000, you can go easily to that level. Okay. So, if you really want to have some serious concentration, you have to go 3-dimensional concentrator. And again here these numbers, if you have some sense of these numbers, then you will have, like if somebody says I have a parabolic trough which is a 2-dimensional concentrator, and by that I am achieving a concentration of 500, you just say that you are lying. That is simply impossible. The theoretical limit is 212. So, you cannot go beyond that whatever you do. Okay. So, that kind of intuition is important, and I wish that you can inculcate that from this course. Okay. So, that is all about the theoretical limit. Now, for the concentrated solar collectors, if we do the thermal performance analysis, what things will be different? Okay. Because the flat plate collector, even including the air heater, we have covered in very detail, but here we are not going to cover all the details, but we need to find what are the salient features or what are the salient differences if you consider a concentrated solar collector and a flat plate solar collector. Okay. So, thermal performance if we want to see, the general guideline will be exactly the same as that of a flat plate collector, because again you are having some absorbed radiation, you are having some losses, and you are having some useful heat. So, the general guideline will be the same, only the intensity is much higher. Okay. So, what things will be different? So, salient differences, if we want to say, the first one is the shapes and designs are widely variable for concentrated collector. Okay. So, shapes and designs, that means geometry is important. We have seen that while we have looked at the liquid flat plate collector and the air heater, okay, and the differences we have looked at. Okay. So, if for concentrated collector you have wide variability in terms of shapes and designs, then those will be different as well. I mean, that will tell you what would be the thermal resistance circuit and all those things. Okay. So, that thing is there. So, it is first thing is that it is difficult to generalize the analysis. For flat plate collector, we have certain predictability of what will be the design, if it is a liquid collector or if it is a air heater. Okay, but for concentrated collector, the designs are so variable that general formulation is difficult. Second salient feature is the temperature is very high compared to the flat plate collectors, and that means both the losses. So, first of all, the losses are higher, okay, because temperature is high, that means the loss to the ambient will be higher. Okay. And the radiation term dominates over conduction or convection terms. What do we mean by that? You have several losses, right? One thing is conduction through the edges, convection through the air layer, and you have a radiation term. Now, radiation term depends on the fourth power of temperature, right, and both conduction and convection terms, they depend on the first power of temperature. So, that means when the temperature is higher, the radiative term will be dominating, right, because this radiation is Tp to the power 4 and conduction or convection, both of them are Tp to the power 1. So, that is why the radiation term will be dominating. Okay. So, what would be the consequence? That the iterative evaluation of the radiative heat transfer coefficient, which is HR, is more important. So, we have seen that whenever you have a radiative term, we have to guess the temperature of the plate and then you find the radiative heat loss from there, and then you come back, find the temperature again and see how much did it change. Okay. And this iterative procedure is more important when the radiative term is dominating. So, in this case you have to do several more steps of iteration, then only you will have a converged heat transfer coefficient for radiation. Okay. Then the third point, the third difference here is the edge effect is significant as we have less area. So, what is the point of concentration? The absorber area is much reduced, that is the point of concentration, right. Otherwise, if you have a very large absorber, then you can as well use a flat plate collector geometry, okay, no concentration is required. So, when you reduce the area and that area reduction depends on the concentration ratio, the edge effects will be more important, right, because the edges constitute a significant portion of the total area. So, these are the major differences. Now, before we proceed, we should have clear understanding about few terms which are particular to the concentrated solar collector. First thing is aperture. Okay. Aperture is what? It is the plane opening of the concentrator through which the solar radiation enters the system. So, it is just like the aperture of a camera, the area through which the light comes in the camera, that is called the aperture, and you can control it depending on the amount of light you want inside the camera. Okay, here also aperture of a concentrator means the plane that is allowing the solar radiation to come into the system. Okay. Then the concentration ratio, which is nothing but the ratio of aperture area and the absorber area. Okay. And the whole point is that it has to be greater than 1. So, the CR is greater than equal to 1. When it is equal to 1, we do not call it concentrated collector, we call it flat plate collector. Okay. The next term is called the intercept factor. Often we designate it with symbol gamma. What is that? It is the fraction of radiation, whether it is, the concentration can happen through different optical phenomena. Major are refraction or reflection. So, whether it is reflected radiation or refracted radiation, okay, that is incident on the absorber. So, we will see that it will be important that all the radiation that are going through the aperture and then getting refracted or reflected to be focused to the absorber may not reach the absorber. So, only a fraction of that will reach. So, ideally we want all the radiation that are passing through the absorber reaches the passing through the aperture reaches the absorber. Okay. But in reality this intercept factor will be less than equal to 1. So, this will be less than equal to 1. Okay. Another important jargon for the concentrator is the acceptance angle. We call it 2 theta A, just like theta S, which is the half angle subtended by the solar disk. Here we have theta A, which is half angle or half acceptance angle. Okay. So, acceptance angle is 2 theta A. So, it is the angle over which beam radiation may deviate from the normal direction to the aperture plane and yet reach the absorber. So, what does it mean? So, there is one particular geometry which we called compound parabolic dish, where you have this is the aperture area, okay. This is the aperture plane and this is the absorber plane. Okay. So, it depends, of course, if the solar radiation is normal to the aperture plane, it will get reflected here and it will reach the absorber. But the acceptance angle is what? If the direction of ray is like this, okay, even then a fraction of it will reach the absorber. So, the angle, angle between the normal and the actual solar beam direction that the particular collector can accommodate, the particular collector can accommodate, that is the acceptance angle. So, basically the acceptance angle here would be the total deviation that it can accommodate, and that will be 2 theta a, okay, and half of that will be theta a. Okay. So, here what we can say, that collector with large acceptance angle require occasional adjustment, but has low concentration ratio. So, one limit we can think of the flat plate collector, which is already familiar to you. So, flat plate collector, you have the acceptance angle to be 180 degree. So, from whichever angle it comes, it can absorb a portion of it. Okay. So, their acceptance angle is huge, but you can keep it fixed, you can have like occasional adjustment, but the concentration ratio is the lowest, that is one. For this particular example that I have seen here, I mean shown here, here also you can have concentration ratio about 6, 7, 10, okay, low concentration ratio, and it gives you a certain acceptance angle which is less than 90 degree, but significantly higher than 0 degree. But most like the parabolic trough or parabolic dish, they have 0 acceptance angle, because you have to have normal radiation on the aperture, then only the concentrator or the reflector or refractor will work and deviate the sunlight in such a way that it reaches the absorber. Now, how to classify these concentrated collectors? There are several possible ways how we can classify. Okay, first one we already talked about, whether it is a reflecting type or a refracting type. So, it is possible that there are lots of reflectors and all of them are reflecting to a certain point. That is how the concentration is getting achieved, or a large surface, each portion of the surface is reflecting the solar radiation to a certain point or certain area. So, that is how the concentration is achieved. So, the basic principle of different reflecting planes all targeting one small area. Okay. That is how the reflecting type concentrator works. And refracting type is very common. You have seen that when in your childhood, I am sure you have done this experiment, that you put a magnifying glass under the sun and you concentrate it in such a way that you can even burn a piece of paper, okay, or a piece of cloth. So, this is the lens based concentrator. A basic version you can see in case of a magnifying glass. Okay. If you have not done that experiment in your childhood, please go back and collect a magnifying glass and do that. It is really fun. The second kind of classification that we can have is whether it is a imaging or non-imaging. Okay. Imaging means you will actually form an image of the sun on the absorber. After whatever you are doing, reflection, refraction, there will be a image formed on the absorber. And non-imaging means it is all blurred, you do not have a image of the sun. So, whenever you have diffuse radiation in action, you have a non-imaging thing, because diffuse radiation does not give you the exact direction. So, that means you do not form a clear image of the sun. Okay. So, such as the compound parabolic trough or compound parabolic collector, parabolic concentrator, that is a non-imaging kind. An imaging kind, you can say that any parabolic dish, you can say, and it works only with beam radiation. The diffuse radiation does not take part in the concentration, and that is why it forms a completely clear image. The third kind of classification we can have is line focusing or point focusing, which is also called the line focusing, means it is a two-dimensional concentrator. We have talked about it earlier when we have looked at the theoretical limit of two-dimensional concentrator and three-dimensional, and point focusing is your three-dimensional concentrator. Okay. And two-dimensional, if you want to take the example, you can take it as parabolic trough, which we will see just after this one, and three-dimensional concentrator is something of a point concentrator, you can say the central receiver tower, or you can say Fresnel 3D concentrator. Okay. So, these are different ways you can classify the concentrator optics. And in case of the difference with the flat plate collector, you can have that we have two areas, two relevant areas for concentrated collector. What are they? One is the absorber area or plate area AP, and other one is aperture area or AA. So, this is the absorber or plate area, and this is aperture area. So, if you remember the flat plate collector, we had only one area AC, the collector area, or we have also written AP. Okay. So, there were no different areas. Okay. So, what would be the difference? Under steady state, we have seen that the useful heat gain, the rate of it was AAS minus the rate of heat loss through the overall area. Okay. So, here the absorption that is happening or the amount of radiation that is coming in is multiplied by AA or the aperture area. So, here the QL is your UL into AP, because now the loss is happening from the absorber area, TPM minus TA, right. So, now if you put that in the above equation, and you can have AA multiplied with S minus UL by C. C is the concentration ratio. Okay. So, C is the concentration ratio, which is nothing but AA over AP. Okay. So, that factor, this factor is new addition for the concentrated collector, isn't it? Earlier you had only one area and you did not have any factor C for flat plate collectors. Okay. So, now we will do the analysis for the most common parabolic trough collector, which is the most common concentrating collector. Okay. So, we will look at parabolic trough collector. So, first let me show you how does it look. Yes. So, here you can see this is an array of parabolic troughs. Okay. So, how do they look? You have a parabolic surface which is long, and at the focal point you have the tube which carries the fluid and gets heated by the collector. Okay. So, what is happening here? You have the solar rays are falling on this and then getting reflected onto this focal plane where the pipe is running. Okay. That is how the parabolic trough collector works. Okay. So, now what kind of collector is that? It is an imaging collector, right, because it does not allow the diffuse radiation to dictate the concentration. It has to be tracked perfectly. So, for any imaging collector it has to be tracked perfectly, and beam radiation is needed to be normal to the aperture plane. Okay. And another way you can say it is a two dimensional or linear concentrator, because all of them, all the radiation is being focused to a line where the collecting tube is there, but it is not being focused to a point. So, you can also call it a line focusing system. Okay. And also it is based on the principle of reflection. Okay. So, it is a reflecting collector, okay, not on the principle of refraction, but the aperture is nothing but a plane which is reflecting. Okay. Now, if we do the optical analysis of that, first thing we can draw that, let us say that this is the parabolic surface, okay, and this is the point of focus. So, let us say this point to be F, and the midpoint of that surface I am just drawing half of it, and the other half will be symmetric. Okay. So, if this is the parabolic surface, parabolic reflecting surface, okay, and this is the focus, okay, focus of that parabola. Now, let us say that B is the end point of it, okay. So, this point B is called the rim. Rim means the furthest point from the center. So, this is the rim, and the radius at the rim is called RR, that means rim radius. Okay. At any other point you can draw, and that radius is R, and that R is changing depending on where you are on the parabola. Similarly, the angle that the rim point subtends, this is called the rim angle, okay, and at any other point you can draw the angle which is phi, and let us name these. So, this is the focal distance F, okay, and if we draw a perpendicular from the rim point to this focal line, let us name this point to be C, and also let us say that this is the x direction and this is the y direction. Okay. So, here what is the aperture? Aperture is this BC, right. So, we can, so this is half aperture actually. We have drawn half of the parabola and this is half aperture. Let us say this is A by 2, okay, where A is our aperture length. And please note that this figure that we have drawn, this is the plane is actually running perpendicular to the plane of the board, and that is why it is a 2-dimensional figure. Okay. We have just drawn a slice of that extended plane, and that is a 2-dimensional plane. Okay. So, let me write that parabolic trough is running perpendicular to the plane of the board, and the receiver is at the focal point F. So, again the receiver is also running perpendicular to the plane of the board. Okay. So, now what we can write, this equation of the parabola, from the drawing we can directly write this will be y square equal to 4 f x. F is the focal length, okay, this is the focal length. Okay. Now, you can see that the tan phi r, so tangent of the rim angle phi r, which is nothing but BC over FC, Okay. So, BC is this one and FC is this one. So, that is the tan of phi r is equal to BC is nothing but A by 2 and FC is nothing but, I mean FC is FC, we do not have any exact form for that so far. So, now we need to find FC, which is nothing but F minus AC. You can see here F is AF, okay, that is the small f, and FC is small f minus AC, and AC is what? Is Ax at y equal to A by 2. Let us see that. So, AC is nothing but x is in this direction, x at y equal to A by 2, is not it? So, now what we can do? We can put this f value, which is y square divided by 4f, that is from the equation of parabola, at y equal to A by 2. So, that gives us A square divided by 16f. Okay. So, we have obtained AC. So, that means FC is f minus A square by 16f, which is 16f square minus A square by 16f. Okay. So, now this tan phi r we can write A by 2 divided by FC, and if we put FC value here, then by simplifying what you can get is 8f by A divided by 16f by A squared minus 1. Okay. And also sin phi r you can find, which is A by 2 divided by RR. So, not only the rim angle, but the rim radius we want to know. Okay. So, let us involve RR here. Okay. So, what we can write? Phi r, either you can write in terms of tan inverse of 8 f by A divided by 16 f by A squared minus 1, or you can write sin inverse of A by 2 RR. Okay. And we can also show that this radius at any place you can write in terms of 2f divided by 1 plus cos of phi. So, this is relationship between the radius of the parabola and the angle of that particular angle corresponding to that particular radius. Okay. Now, look at how the image is formed by the reflection based concentrator. Okay. So, suppose we have this particular parabola, as we have seen earlier, this is x and y, we have certain here, let us say the focus point is here. Okay. So, let us say we have a plane at the focus point. So, at the last point or the rim point, let me make this smaller. Okay. Yeah. At the rim point, what we have? We do not have a single solar ray coming onto this point. We have a cone a 3-dimensional cone that is coming on the rim point, because sun is a circle, sun looks a circle from that point B. Okay, this is point B, this is point A. So, at point B sun looks a circle, at any other point it will have a cone of light that is falling on that. Okay, and that cone when gets reflected, it will maintain that cone form, conical form, right. So, what will it do? So, let us say this is the reflected cone and this is the incident cone. Okay. So, you can see that across the focal point, the distance at which this plane cuts are different. This is a smaller distance compared to the other side. This is a larger distance, right, or longer distance. Okay, and this is the focal point. So, if you look closely, that the conical light ray after reflection creates an asymmetric image on the focal plane, isn't it? This is the focal plane, this is our focal plane. So, what would be its consequence? If we have a certain receiver there, so the image that will be created will be asymmetric across the focal plane. Okay. So, now if we just look at that focal plane, okay. So, from one side, one rim angle, it will have, let us say, this is the cone that from the right hand side focal point, and there will be another one which will be from the left hand side focal point. Okay. So, this is left side rim point, and this is from, or this is from left side rim point, and this is from right side rim point, right, and from the middle you will have in between these two. Okay. So, this is from the midpoint of the parabola. Okay. So, you can see that ultimately if you have a 2-dimensional parabolic trough, then the image that will form, that will be symmetric, but from one point if you look at it, the image will be asymmetric, because now you can see the length of that image, the total length of that image will be this, right. So, the total length of the image, but you can see that in this region, so in this region all the points on the parabolic reflector are contributing. So, here in these or in this region all the points on the reflector are contributing, isn't it? But beyond that all the points are not contributing, few points are contributing. So, the intensity will be different. You have an image formed on the focal plane, but the intensity will not be equal everywhere. At the middle it will be higher and towards the edge it will be less. Now, you can have different kinds of receiver. Okay. So, on the image focal plane how the image will form we have written, but now you can have either a plate kind of receiver, you can have a sphere kind of receiver, not sphere but circle, okay, and a semicircle, that is also possible. So, this is plate, this is tube, or this is semicircular tube. So, these different kinds of receivers you can have, and what we want? We want that the interception is maximum. So, we want the intercept factor gamma is close to 1. That means, all the radiation that are getting reflected from the parabolic trough should reach the or should intercept the receiver. So, we will see all these details, how the image forms on the focal plane and how the different receivers will affect in the next class in detail. Thank you very much for your attention.